Hello and welcome to another video on the topic of equations and inequalities, the second one of the series. So the first lesson we recapped lots of the things we should know by now from GCSE, and today I'm going to have a look at solving them and how these link to the graphs of inequalities, extending into where it's not just two lots of simultaneous linear equations, but also looking at where we have a quadratic and a linear. So before we start proper, there are 4 warm-up questions as ever. So here they are, have a go at these. Question 1 and 2 is quite a special set of questions, which we'll see in a moment. Question 3 and question 4, a bit more standard. But please have a go at these first, check your solutions using the video if you need to, and then make any corrections where necessary. So let's have a look at question 1. So question 1, it says, starting at the top left and moving to the right in rows, write 6 consecutive integers in the boxes below to form a pair of simultaneous equations. So what number you start with is completely up to you. You could go, for example, 1, 2, 3, 4, 5, 6, or 100, 101, 102, 103, 104, 105. It's entirely up to you. So what I've picked here, I'm going to start at 10 and go up in consecutive integers. So 10, 11, 12, 13, 14, and 15. Okay, so for part 2, what we need to do is to solve that pair of linear simultaneous equations I just created, and then compare answers to other people and see what we notice. So just to remind of what I put in the boxes for question 1, I started at 10 and moved up 11, 12, 13, 14, 15. So what I'm thinking I could do is I could eliminate the x's. I could multiply the top equation by 13 and the bottom by 10. That would give me 130 x's in each, which I can then eliminate. So times in the top by 13, we get this. Times in the bottom by 10, we arrive at this. What we can now do is subtract the bottom equation away from the top. So if we do that, the x's cancel. The y's, 143 of them minus 140 of them, we're left with 3y. And 3y equals 156, take away 150. So 3y must be 6, therefore y equals 2. Now we know that y equals 2, we can substitute that back into one of the initial equations. And so if I sub y equals 2 into the initial top equation, we end up with 10x plus 11y, 11 times 2 is 22, equals 12. So then we have 10x is going to equal 12 minus 22, which is minus 10. Divide through by 10, we get that x equals minus 1. So my set of solutions is x equals minus 1 and y equals 2. So what did you get? Do you notice anything? What I'm hoping you've noticed is you ended up getting exactly the same. If you were to ask your classmates or anyone else, you should find, in fact, that you all, weirdly, end up with this set of solutions. X equals minus 1 and y equals 2. As long as you start with any whole number, then go up in successive steps. So why is that? Well, this is one as an extension for you to prove algebraically. So doing it algebraically, I've put a little animation here on this next slide to show you what's happening. Okay, so in the red, I'm starting with the first integer being a, then a plus 1, a plus 2. Then the bottom equation, I put a plus 3, a plus 4, and a plus 5. So the red is the general form of the first equation, the first line. The blue one I've highlighted is the general form of the bottom equation in the second row. So you can look here, they're always intercepting at the point minus 1 and 2. So despite these two lines going in different places, they're always rotating about this point at minus 1, 2. How weird is that? So let's see if you can prove it algebraically as an extension if you finish the main activities. That really is rather cool. Moving on to question 3. So we've got this set of axes provided below, we need to sketch the graph of these following two equations. Sketch the graph of the following two equations, labelling all points of intersection with the coordinate axes. So what I'm going to do first of all is take this top one and see if we can factorise it. If you've got a quadratic we can factorise, best thing to do is to do that. So we need to find two numbers that multiply together to give us 10, and when we add them up, give us minus 7. Well, those two numbers could be minus 2 and minus 5. So what's going to happen is we're going to have a x-axis intercept at both 2 and 5, and if you sub in x equals 0, the y-axis intercept is 10. So it's also worth saying that when x is 0, y is 10. And so we can graph this one here. Here goes nothing. I'm terrible at sketching graphs, as you know by now. And up again. So what we have here is, that's 2, that's 5, and this one here is 10. Meanwhile, where we have y equals x plus 3, we know that the y-axis intercept of that one is going to be at 3. So we can pop this in as well, just using a straight line. This is a straight line with gradient 1. Okay, so this one's going to be something like this. Okay, not drawn very well, admittedly. In fact, what I'm going to have to do is extend my x-axis. So thank God I've not said this is drawn to scale. And so the x-axis intercept is when y is equal to 0, so 0 equals x plus 3. It will intercept the x-axis at minus 3. Yes, I know, that's nowhere near to scale. It's shoddily done, but at least I've got the points labelled on there. And so that's the graph of both of them. For question 4, without using a calculator, we need to solve this equation. So x squared minus 7x plus 10 equals x plus 3. We can subtract x plus 3 from both sides, and we get x squared minus 8x plus 7 equals 0. This can then be factorised. So two numbers that multiply together to give us 7, when we add them give us minus 8, we could have minus 1 and minus 7. Therefore, these are equal to each other when x equals 1 and x equals 7. As solutions at x equals 1 and x equals 7. But if you remind yourself in question 3 what we graphed, the two graphs we put on the axes were y equals x squared minus 7x plus 10, and we did the graph of y equals x plus 3. And so this equation here links exactly to the points of intersection on the graphs we just drew. So just to remind you what we just had, we had these here. So this is just done using a bit of graphing software, Desmos, which is great by the way, and this is done much better than what I could have done myself in my shoddy sketch. And so the solutions we just worked out were x equals 1 and x equals 7. So we can add these on here. So x equals 1 and y equals 7. Sorry, x equals 7. So 1 and 7. But then if we remind ourselves of this blue line was the line y equals x plus 3. And so when x equals 1, y would be 4, because 1 plus 3 is 4. And when x is 7, y would be 10, because again 7 plus 3 is 10. And so if we were to solve this in terms of x and y, this could be extended to solve the graphs we drew in question 3 simultaneously. So although this isn't part of question 4 of the warm-up, it's just nice to show how this naturally will extend from taking one equation and extending it into a pair of simultaneous equations. And so in other words, these graphs would meet at the coordinates 1, 4 and at 7, 10. Let's move on now to the main portion of the lesson. So question 3 and question 4 in the warm-up, we just showed there that quadratic simultaneous equations are not restricted to just one pair of solutions. So in the case I just showed, we had x equals 1, y equals 4, and as well as that, the coordinates x equals 7 and y equals 10. So what we're going to do here is explore this idea a bit further by sketching quadratic graphs and straight lines on the same pair of axes. Before we do that though, we need to consider the possible numbers of solutions for a straight line and a quadratic graph. So one case we have is where the straight line doesn't intersect the parabola at all. So for example, it could be like this red line here. It just doesn't touch the parabola at all. If there's one point of intersection, that's one and the same thing as saying that the straight line is tangential to the parabola. It just scrapes it at one particular point. So one example, just if I were to shift this red line up just to touch the minimum, we'd have something like this. It would have one root at, in this case, the minimum. It's not to say that this tangent has to be perfectly horizontal. We could have different tangents, for example, one going diagonally that just scrapes it at, for example, this point. The final option is if it doesn't have 0 points of intersection or 1, we could have it where we have 2 points of intersection, like so. So this one would have a pair of solutions here and also here. So let's see now if we can put this into practice by solving some worked examples. So let's see here what we have. So we need to solve these pair of simultaneous equations in part A, where we've got y equals x squared plus 3x minus 2 for one, and for the other, y equals 5x minus 3. So what we need to do here is to substitute in that y equals 5x minus 3 into the top equation over here. So all I'm going to do here is just highlight 5x minus 3 in place of y. We can then take it further and then solve. So using that idea, what we're going to see is that this top equation is going to become 5x minus 3. I'll just get this pen here to work. So 5x minus 3, which is y, by the way, of course, equals x squared plus 3x minus 2. Just replacing y with the expression for y, which is 5x minus 3. So if we subtract 5x minus 3 from both sides, we can set this quadratic expression equal to 0. So we have x squared, take away 5x from 3x, we have minus 2x, minus minus 3, essentially adding 3 to the minus 2 will give us plus 1 equals 0. Now this will factorise into a perfect square. Think of two numbers that multiply together to give 1, and when we add them you get minus 2. That's going to be minus 1 and minus 1 again. So x minus 1 brackets x minus 1, essentially x minus 1 all squared equals 0. So we can see we have one solution here. So therefore we're going to have x equals 1, which is our solution. And if we substitute x equals 1 into this for y, we can see that y is going to be 5 multiplied by 1, which is 5, minus 3, which is 2. So our solution is x equals 1 and y equals 2. And that's the solution to this pair of simultaneous equations. Next up, slightly harder, we have part B. So we can either substitute in an expression for x or an expression for y, whichever is simpler. What I'd suggest is simpler is rearranging to make x a subject and substituting in an expression for x. So for this bottom equation, we can see that x is going to equal 3 minus 2y. What we can do now is we can substitute this expression for x in place of x in this top equation. So the top equation is now going to become something that looks a bit different. So x squared is going to be 3 minus 2y all squared. We can have plus 3, lots of x, which is 3 minus 2y. Then y at the end equals 0. So at this stage, all we've done is just substitute in an expression for x in place of x itself. So let's just rearrange this ever so slightly to make it easier to read. So we have 3 minus 2y all squared. 3 multiplied by these brackets multiplied by y. I'm just going to put this y next to the 3. Just makes it read in a more obvious way to us. Equals 0. We can now expand this out and start to manipulate it. So 3 minus 2y all squared, we square the first term, so square the y, so square the 3, we get 9. Then 3 times minus 2y is minus 6y. We double that product to get minus 12y. And finally square the last term. So minus 2y all squared gives us positive 4y squared. So this bracket here has become this. Then we can expand out this bit here. So 3y times 3 is 9y. Then 3y times minus 2y. 3y times minus 2y gives us minus 6y squared. So this has become that. We then set that equal to 0. So let's simplify this side. So 4y squared minus 6y squared, that becomes minus 2y squared. Minus 12y plus 9y is minus 3y. And then plus 9 equals 0. This looks a bit of a mess because the squared term is negative. So if we multiply everything by minus 1, we get 2y squared plus 3y minus 9 equals 0. This will now factorise. We can use the AC method to factorise this. So if we multiply the 2 and the minus 9 together, we get negative 18. So now we need to think of two numbers that multiply together to give us negative 18. And when we add them, we get positive 3. So with a bit of thought, you'll hopefully see that these two numbers are going to be positive 6 and negative 3. So what this means we can do is this 2y squared plus 3y minus 9, we can factorise this. We can partition the 3y into a 6y and a minus 3y. And minus 9 equals 0. We can now factorise these two pieces into just one bracket. So 2y squared plus 6y. So this is a common factor of 2y. And bracket y plus 3. This here, minus 3 and minus 9 have a common factor of minus 3. And in brackets we get y plus 3 yet again equals 0. So that now becomes 2y minus 3 all in one bracket multiplied by y plus 3 equals 0. So therefore either y is going to be 3 over 2 or y is going to be negative 3. So we've got one solution, we've solved for one variable. We're going to then need to find out what x is going to be for these values of y. Now we've got these two values for y, we can remind ourselves of the second equation of these simultaneous equations, the linear one. And that equation was that 2y plus x equals 3. So now we have these two different values for y, we can substitute these values of y into this linear equation to work out the corresponding values of x. So first of all, we can substitute in when y is 3 over 2. 2y is 3 over 2 times 2, which is 3. So we'd have 3 plus x equals 3. In other words, therefore x would have to be 0. So the first one, we get x is equal to 0. So we can write this in. So therefore y equals 3 over 2 and x equals 0. So that's the first set of solutions for both y and x. Next we can substitute in the option where y is minus 3. So then we'd have 2 times y, 2 times minus 3, which is minus 6, plus x equals 3. Then by adding 6 to both sides, we get that x equals 9, and that gives us our second solution set. So we can write this in, and then we've completed the whole thing. And there we go. So now it's over, as ever, to you. So if you could please try these questions on page 41, exercise 3b, and you know the drill. If ever you get stuck, check your answers on the back or ask a peer. If that isn't helping enough, or you still find yourself struggling, ask me in class, on an email, or on this YouTube video. So thanks for listening, and you'll hear from me again in the next video. Thanks for now. See you soon.